Awesome. Good to see everybody. Great to go last, get to wrap it up, no pressure, right? So today I'm going to talk to you about hyper-scalable subnets, or basically what I've been working on, kind of help alongside of everything else we've been doing. But yeah, it should be fun. So it gets a little technical, so this assumes prior subnet knowledge for sure. So if you don't have that, like watch some of the other talks I've given on the topic and then come back and watch this one later. But yeah, we'll see how this goes. So I'm Patrick. I'm the head of engineering at Ava Labs. So what I joke around with all the other engineers at Ava Labs here, I think a bunch of them are up here, is I get to take a lot of credit for their work, and then they get to work late nights. But no, I'm doing the same thing with them. I think some of the people at Ava Labs are some of the smartest people I've worked with, and I think we've had a lot of fun building some awesome stuff over the last year or so, and years before that, but since I last talked here. And so, yeah, so that's that. So I think Nick already covered this, but I was joking around with someone, and I was like, yeah, last time we were at Summit, there weren't even any subnets live yet on mainnet. And so my talk last year was like, oh, trust me, like, there's all this crazy subnet stuff coming. Like, just wait, it's going to be awesome. And people are like, okay, yeah, sure, like, it's going to be great. And then now to see all of it launch and everything that came after that, it's been great. So as Nick called out, we have a bunch of folks live on subnets now, but like, I mean, I think what the more interesting takeaway is the amount of computation that's actually happening on subnets relative to other blockchain networks. So there's more than 900 billion gas used per day across all subnets on Avalanche. Now, you may be saying, like, well, what's gas? Maybe you're not super familiar with that. Well, 900 billion gas is more than Ethereum uses, more than Polygon uses, and more than Binance Chain uses. So as an architecture for launching, launching EVM-related things, Avalanche uses the most gas out of any EVM ecosystem. So in terms of like what it means to actually provide interesting block space to use and compute if you're launching blockchains, I think it's a super interesting growth curve we've seen here, basically from original launch of the network, people still figuring things out, all the way up until when the subnets really started to launch, and then from there it's been really cool to see all the growth and things people have been doing on subnets. Again, Nick stealing all my thunder with what's happening on Fuji, so really cool to see all the growth there. It looks really exciting, and again, thanks to the Vaults guys for kind of mapping this out. But where that takes us is, well, what are people running? It's just EVMs. And so we have EVM precompiles, we have EVM this, EVM that, and the joke always has been, well, isn't Avalanche just a Geth fork or like something like that? And so then there was a funny tweet that someone sent a while ago, which is like, in an effort to like break away from the EVM mold, Avalanche has decided to launch more EVMs. And so I thought it was a pretty funny leap with what people have been doing. And so what do we do as engineers in trying to figure out what to do next? Do we do more EVMs, or do we try to really change the page and how we're actually thinking about what we're doing? And so the rest of this presentation really is about what we're doing that isn't the EVM. And so the awesome design team we have put together this great GIF, which is, if you've seen the movie Spaceballs, which is a hilarious movie and mock of Star Wars, this is like ludicrous speed, and they replaced Hyper SDK there. And so the project we've been building, I'm actually really happy this GIF works. I didn't know, like doing a presentation, if the GIF was actually going to work, and it was just going to be stuck on Lightspeed. But so the project we've been working on and that we released a few months ago is called the Hyper SDK. And so when we released it, I was talking about, well, where does the name actually come from here? And so for a long time on all parts of the platform, things that you have seen and haven't seen, our focus has always been performance, and really performance above all else. And so using the name Hyper, kind of describing what we're working on, is really a reminder each time we're working on it, each time we're talking about it, what our real focus is, which is trying to hit performance thresholds that get really interesting for all sorts of new types of blockchain applications that wouldn't necessarily be possible on other virtual machines you could run on Avalanche. So where this comes from and where we're going with this is to say, great, you're interested in launching your own subnet, and maybe the EVM is a great place to start, but maybe you want something different. Maybe you want a different trade-off in how blockchain systems are designed, or want to contribute your own virtual machine. But the problem ends up being, when we were going through this process, was that, yeah, we were like, awesome, custom virtual machines are great, like, we're excited to see people use it. And then we're like, there's so many options, anything you can build. But the feedback we got was that there were too many options and too many things to build. And so the Hyper SDK takes the best ideas we have found, at least in building on top of Avalanche, and puts those in an SDK that anyone can extend when they're building their own blockchain. And so the idea is that we can take the best algorithmic choices that we think work for Avalanche, put those behind the scenes, and then expose a much simpler interface that you can use to build blockchains. And so I've given a number of talks on like exactly the sort of interface you get as a virtual machine builder, and we're still working on a lot of the documentation there to make it even easier. But this talk is going to start to go into what actually makes it faster and what actually makes it more performant for the use cases we care about. And so I'm going to dive into a few major design things and then talk about where we're going from here. So the first thing that we built that is super important to anything that we're doing on the Hyper SDK is the introduction of this thing called the Merkle DB, which is a path-based radix tree. So for people that don't know what that is, basically in any virtual machine environment, you have blockchain state. Now that state could include anything. The simplest thing I usually describe it with is balances. So the balances of everybody on the chain. Well, if you just store that data in a database, you can't actually let people sync to that state, because they would have to then re-execute everything that's happened to that point. So people tend to use some form of a Merkle tree or Merkle tree to actually store that data, because then you can quickly sync to it without actually having to re-execute all prior blocks. So because that actually manages all your state, or is a data structure that helps to manage all your state, it has to be wicked fast and wicked efficient if you're going to achieve any scale or throughput. If this is really slow, it doesn't matter how fast I can execute transactions if this takes 15 seconds to update at the end of every block. So the first thing we started working on was actually this generic Merkle database store. And so this currently powers the database and state sync on the Hyper SDK, but will also power state sync on the X chain and the P chain by the end of this year. And so the other really cool thing, or I guess the other thing I want to call out, is it's really good at storing just the current state. Now that may sound like an obvious problem to you, right? Like if I'm creating a database to track the current state, it should be good at just tracking the current state. Well, actually, no. Most of these sort of like tree-based databases will actually try to minimize the number of duplicate nodes they write to disk. And so every time you write a root, you only write new roots to, like when you write a root and write all the nodes that you've changed, you only write the new nodes. And so at any point in time, you actually don't know which nodes on disk still apply to the current state. And so we've changed dramatically how the nodes are actually stored on disk, so that at the end of each block, we actually know which nodes can be deleted and then restored or like written to disk. And this means that like as you process blocks, your state isn't just growing with a bunch of junk that you have on disk. If you want to read more about this, and this is where we're spending a lot of time these days, there's an article that one of our engineers wrote that you can check out to learn more. The next one, it's always fun when I get to build new diagrams, because a lot of the people on the engineering team are like, oh, now I get what you're talking about. So the next thing that the Hyper SDK does, which is quite opinionated, is require the use of transaction access keys. So when a transaction is generated, if it knows exactly which keys and state that it's going to touch prior to execution, the virtual machine can then do very intelligent things with sequencing of that transaction and also prefetching of state used in that transaction. And so the important thing here is the keys that you're touching are actually not like the tree keys, but the logical keys in the database, which makes it much easier to pre-compute and actually use. So I have one example here just to kind of share what I mean. So in one virtual machine I wrote, you can mint transactions, or mint assets. And so the state key for that is really simple, which is, all right, if I'm going to touch an asset, I'm probably going to touch the key that's associated with that asset in the database, and then the balance of who I'm actually going to send the money to. Now, what this lets the Hyper SDK engine do is when it's parsing the block, the keys here are the part of the transaction. It can then prefetch the keys
transactions in order from the Merkle DB, store the actual state that is pulled from the database at that time, which is usually actually the biggest bottleneck in execution, and then put those in a queue where they can then be executed asynchronously, and at the very end, generate the root. So this lets you do a bunch of work at the same time instead of just iterating through the block sequentially, which can mean that you can process much more data within a given time if you have more compute. What this looks like, because with this performance engineering, gathering metrics and traces is critical to actually understanding what you need to do, was what it actually looks like in real life to process a simple block on the Hyper SDK. So, you see this prefetch time, and during the prefetch time, it's also executing. You can see that nice overlap. And then at the very end, we end up writing changes. And then you see this huge, I'll talk about this later, the root calculation, which ends up being this huge amount of time that we're just waiting to generate things. And so if the Merkle DB is slow, like I was saying before, this can grow arbitrarily long. And then, well, it looks like you're doing no work, you're just keeping the database up to date. It ends up taking all of this time during block execution. The other really cool thing that the Hyper SDK does is it doesn't use nonces. So if you're familiar with Ethereum or the C chain, you'll be submitting transactions that have some sort of nonce. And a lot of times, many people have encountered this. The price or the gas price will go up. Your transaction's going to get stuck with some nonce, and you got to either replace the fee or just wait indefinitely for it to come back. Well, you don't have that problem with the Hyper SDK, and not only is that a better UX for you, but it's also much more efficient for the actual execution engine because the mempool could be much dumber. Basically, it can say, well, at any point, any transaction can be executed. There's no notion of ordering here. And so it can just, whatever it gets, try to execute it in any order, and it's fine. Whereas if you have nonces, you actually have to execute them in order, and this adds a bunch of extra logic around gossiping, around the mempool, and a bunch of extra complexity. As a byproduct of this, it also has expiry. So transactions that have been in the mempool for some period of time, after some period, will just disappear. This is good for you and also good for the virtual machine that can limit kind of how it prevents replay attack. But I'm not going to get into that part here. The last one is that as we put the Hyper SDK in practice, it's really important that it can connect to the rest of the subnets. And so it also natively integrates Avalanche Warp Messaging. But I'm running up on time, so I'm going to avoid talking about this one. I've already given a number of talks on this too, and I think it's becoming a buzzword for me at least. And so the cool thing you can do, though, with some of this awesome Avalanche Warp Messaging is you can create arbitrary interaction patterns on top of the between different Hyper SDKs. So in this case, I actually implemented Crosssubnet Trading on top of the Hyper SDK. And so I have a demo of this online. You can look at it on Twitter if you want to. But the whole idea is I mint assets on one Hyper SDK. I then send the asset over to another subnet that's also running the Hyper SDK. And on entry into that subnet, it trades the token I'm bringing in for a native asset, which typically if people are moving subnet to subnet, you want to get the gas token on the recipient subnet or destination subnet so you can actually perform transactions there. So this is an example of one really sophisticated thing you can do. But what you probably want to know is TPS. Well, how performant actually is this thing? So a lot of my work now that we have some backbone or backbone to really play off of, is experimenting how hard we can push it on different environments. So last week or 2 weeks ago, we achieved sustained 35,000 TPS for a while. I kind of cut off the end of this thing. But you can notice here, first of all, it stops at 35. And then secondly, it's a little shaky. So why isn't it flatlined at 35 if that's how many transactions I'm actually sending? And so we go into two bottlenecks. So the way that the Avalanche Consensus engine works is that a node will be triggered to build when it's time to build according to Snowman++. And then that build, however long it takes, will prevent, the node will basically say, okay, I'm going to build. It then builds for some predetermined amount of time, or not predetermined, just how long it decides to build for. And then when it's done building, it tells the engine, hey, I'm done building my block. Here are the bytes. And then the engine will then distribute that to the rest of the network. But for another node to actually start voting on that block or even using it, it has to wait to get the block and then verify that block. So you'd say, okay, this is pretty standard, right? Like I kind of showed this out across time. So let's say node 1 starts building at time 0. Let's say it finishes building at time 4. Maybe I should have flipped that, but and then let's assume there's a network delay of like one of these t, and then I now verify it. Usually you can verify a little faster than building because you can do more asynchronous work than when you're building, but let's just say it takes the same amount of time, so I'll be done at 9t. Well, that means that for a single block, the fastest you can actually have it get into voting across the rest of the network optimistically is at 9t. Well, if that happens, you have a bunch of processing blocks. Like if I'm supposed to build after who built me, I can't start building the next block until here because I rely on the state of this block. That's a problem. It'll limit how much throughput you can do because if you start to increase the size of this block, this gets longer, and then this gets longer, and then before you know it, you're starting to see a lot of rejected blocks because the total time to get through the network is more than 5 seconds. So the first optimization we're going to add is what's called streaming activity blocks and checkpoint block routes. So what we're going to start doing is basically break apart the block building process into smaller chunks. Those smaller chunks, we're then going to stream to validators, in this case, still red, and then separate it out into what are called activity blocks and chunk blocks. So activity blocks will just contain transactions. They won't actually trigger any of those root calculation things that I talked about with the Merkle DB. What that means is that as a validator, as soon as you get these chunks, you just start applying the changes, and then you wait for the next chunk. The checkpoint block is really the last activity block, and that basically says, hey, I'm done. You can start working on the next block as you get it. So what this means is the build time's still the same, right? Maybe we can make that faster with other things. But all else equal, that means that you finish verification at 6t instead of, in the last case, 9t, with all else equal. Now, the benefit for that, then, is the delay, the max delay you get is basically the time of one network delay plus one verification chunk. This lets you go a lot faster for the reasons that I described earlier. You can put many more things inside of these blocks. And then you get back to the problem of actually optimizing the build loop, which should add, it should be 30% fewer, period of time for end-to-end voting, which means that you should get, the opposite of that, more blocks per second. The other thing is what I was talking about earlier, which is this calculate IDs thing. So naively, you would think, hey, when I'm verifying a block, I'm going to have a state root that shows up at the end. Well, that state root I'm going to verify at the end of the block. Well, and that's useful for powering state sync. Well, if you do that, you end up having to wait that entire node, root calculation time. Well, what if instead we actually put the block root being the state root of the block, so basically the block root of the parent. What that means is that when you're in this period and you're actually finishing it, you kick off that Merkle root calculation, keep it running in the background, and then don't actually need it until the next block. So you can then wait, if you're not producing the next block, at least a few hundred milliseconds typically before you actually need it. And so that means that then you can start voting even faster. So in this case, and building also gets faster, so then you could probably take off and it would end up being even 1t to the left. So it could end up even being built in 3t in this case, and then verified in 5t. So at that point, you're basically cutting, or basically doubling the amount of build verify cycles you can do across the network. What that means is double the throughput. And so this is just an example of what this block format actually looks like in the Hyper SDK right now. And so just as a reminder, right, this is one example of a custom virtual machine. We're worrying about all of this optimization complexity behind the scenes so that you don't have to, and that when you're actually building your virtual machine, you can just implement the things on top of that. And so, yeah, so I want to give a quick update on we're really playing around with stuff behind the scenes to really get this Hyper SDK up to a throughput that we think is extremely competitive on a $1 per transaction basis for people actually executing transactions, and a $1 per transactions basis for people to actually run these things. But the Hyper SDK aspirations don't really stop just with doing 30 or 40,000 TPS. While performance is the North Star, UX for developers and builders is still really important. And the biggest missing feature in the Hyper SDK is the ability to do arbitrary programs or run arbitrary programs on top of it. And so what we're going to work on after we finish these two optimizations is really looking ahead to a whole new way to think about how you deploy contracts on top of the chain, coupled with the RPC, coupled with the browser. So a lot of people have put a lot of time into this format or assembly format called WebAssembly. I didn't make this diagram, by the way. I don't know where it came from, but I searched on Google WebAssembly, and this looked the coolest. So I took this one here. But the idea here is that WebAssembly is this really interesting portable language, or like portable assembly script or backend for the LLVM compiler that runs near native time, but has really awesome security properties that you'd want for some sort of virtual machine that could run arbitrary programs. Now, you may say, well, you could also build your own backend or your own engine, which is totally true. But the other thing that it gives you is that this WebAssembly format is already compatible with browsers. So every major browser can already run this. Similarly, it's very flexible. So it doesn't have to just be for programs. And so what you can end up doing as a developer is almost create 3 separate modules or one large module that lets you implement a custom RPC layer, so like whatever you want the node to actually serve, a custom browser extension or like browser layer that you're actually viewing in the browser. So like if you build a some sort of really cool contract, you probably want to show it in a specific way, or at least power like extensions to interact with it. So, and then obviously what happens on chain. And so using this model, you can actually create a unified experience that anyone can just integrate out of the box, and then you can also get away with having arbitrary on-chain interaction. And so after we continue working on the performance, this is where we're going to go next, which I'm pretty excited about. But we have a few people working on it now. But I really am excited by the progress we've seen so far on the optimization side, and I think there's still a lot of room to go there. So yeah. So that's really it. If you enjoyed our talk, we're always hiring at Ava Labs. You can come check that out. And then, yeah, that's pretty much it. So thank you for your time, and thanks for coming out. Cool.